Chapter 26 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by elmachina. The Romance of Modern Electricity by Charles R. Gibson. Chapter 26. Electricity in the Coal Mine. Edward I prohibits the use of coal. Early ideas of getting at the coal. First attempts in using machinery underground. A trip down a coal pit. Electric light and haulage underground. The employment of ponies underground. Electric coal cutters at work. Men go with a powerful machine along a narrow passage only 18 inches in height. Is the miner deprived of employment by labour-saving machinery? The application of electricity enables old mines to be reopened and worked at a profit. We are all very familiar with that mineralised vegetable matter to which we give the name of coal, and no one needs to be informed that it is found embedded in the earth in large layers or seams, but a few introductory remarks may be of interest. Although the ancients knew of the existence of coal and were aware that it would burn, they did not seek to make any practical use of it, as there was plenty of wood to be much more easily obtained. The introduction of coal, or as it was at first called by Londoners, sea coal, because it came to them by the sea, met with great opposition. A few years before the Battle of Bannockburn, we find Parliament successfully petitioning King Edward I to prohibit the use of coal in London, as the citizens were offended at the sulphurous smoke and savour of the firing, and at a later date we find that the nice dames of London would not come into any house or room where sea coals were burned. With the increase of industries, such as iron smelting, it became almost a necessity to make use of coal, as the country's forests were quickly disappearing. One quotation from an interesting tract written in 1629 will serve to show how the matter then stood. An ironmaster in the neighbourhood of Durham is accused of having brought to the ground above 30,000 oaks in his lifetime, and if he live long enough, it is doubted if he will leave so much timber in the whole country as will repair one of our churches if it should fall. It was not, however, until the 18th century that coal came to be used in iron smelting. The invention of the steam engine gave a great natural impulse to the use of coal, for it not only became a large consumer, but it also made the winning of coal from the bowels of the earth a much easier task. The first idea of obtaining coal was to open up the ground as is done in a stone quarry. Then followed a system of tunnelling into the bottom of a hill, in which seams of coal were known to exist. Obtained in this way, the early coals would be of inferior quality, being taken from near the surface, so that the stench complained of may have been greater than the smoke to which we are now accustomed. It was soon found that the best seams of coal were buried too deep in the earth to be got at by the opening up of the ground, and there was nothing for it but to dig a deep hole or pit down which men might be lowered into the earth. Mines have been sunk as deep as 3,490 feet, or considerably over half a mile down below the surface. The seams vary from a few inches to more than 30 feet in thickness. Coming to a seam of coal, it is the duty of the miner to cut away the black diamond and send it to the surface, and it is in connection with the cutting of the coal that electricity is already playing a most important part. Till quite recently, it has been necessary to do all the hard work by manual labour, because of the difficulty of carrying energy to any mechanical appliances deep down in a mine. Attempts were at first made with long connecting rods or shafts from an engine on the surface, reaching down to the bottom of the pit. In some cases, even engines and boilers were placed away down in the earth. More recently, compressed air was used, and is still in use. But what a stride we have now made in being able to carry electrical energy from the surface, along a stationary wire, away down into the mine, and into the most awkward coal seams, there to drive a motor attached to a machine. As it is not convenient for everyone to visit a coal mine, it may be of interest to give a brief description of the different ways in which we find electricity serving the miner. Having gone by train into the country, the visitor makes his way to the pit head, where he finds an engine house in which an engine is driving a dynamo and generating current. He first of all notices a cable stretching from the engine house away across the fields, and he learns that this cable is conducting current to an electric motor, placed on a riverbank about a mile distant, and that the motor is there driving a pump which, in turn, is forcing water from the river through a pipe to the engine house. Instead of having a small engine and boiler at the river with someone in attendance, this little motor, quite unattended, is under entire control from the distant engine house. In a separate building the visitor finds another engine, or it may be an electromotor, for raising and lowering the cages in the pit shaft, and if he is of nervous temperament, he may drop a hint to the engine driver that he has no desire to feel the sensation of flying down the pit shaft at full speed. Getting onto the cage, the novice is warned by the manager to take a good grip of the iron bar overhead, and as soon as he is plunged into darkness he is rather alarmed, if it be his first experience, to hear a sudden deafening clatter immediately overhead, which he is informed is caused by the policeman, this name being given to a very heavy trap-door which falls over the pit mouth as soon as the cage enters the shaft. It seems a long journey to the pit bottom, but the engine driver is putting the stranger down more cautiously than he does the experienced miner. If the pit be one of 2,000 feet in depth, the visitor welcomes the bump which assures him he is at the end of his downward journey. If the explorer has expected to find himself in a large, spacious underground coal quarry, he is disappointed. Even if the mine be an important one, there is no more open space in the pit bottom than one finds in a large room, and from this space a number of tunnels or roads lead off in different directions. The coal here has not been touched, except to make these passages through it, for it is necessary to leave the earth as solid as possible all around the pit shaft. No matter how valuable the coal seams may be, the miners must travel 200 or 300 feet along these main roads before they touch any coal. Footnote: the descriptions refer to the working of a mine on what is called the longwall system, consecutive slices being taken off the whole face of the seam. End of footnote. Before setting off to explore the mine, the visitor is attracted by the noise of machinery, and in this particular mine he has no difficulty in finding his way about, as the bottom and the main roads are equipped with incandescent electric lamps connected to the dynamo above ground. He finds the noise to come from a room close to the pit bottom, where an electromotor, also connected with the dynamo above ground, is driving a number of large drums, each of which is hauling in or paying off a long wire rope. Each of these haulage ropes passes right along one of the main roads, lying between the rails of a narrow-gauge track, so that the little trucks, called hutches or tubs, may be hauled to the pit bottom and then sent up the shaft to be unloaded. The motorman has a series of electric bells of different sounds, each one representing a different road, and as two bare wires are led along the roof of each main road, the miner can make the wires touch each other at any place, and thus signal to the motorman to haul in his trainload of coals. Touching the wires together is equivalent to pressing a bell push. In this case the electromotor is stationary, and merely hauls in the wire rope, thus propelling the hutches, but in some mines, such as American drift mines, where an inclined tunnel is run into the mine instead of a perpendicular shaft, the motor may be carried on a small truck, thus forming a miniature locomotive, and receiving power from a fixed conductor overhead, just as an electric tramway car does. Ponies are still used underground for hauling the hutches along the side or branch roads to the main roads, and at present it looks as though these could not very conveniently be replaced even by electricity. But it is quite a mistaken idea to suppose that these ponies are blind, or that they are in any way ill-used. My experience on visiting mines, where sometimes as many as 30 ponies are at work in one pit, has been to find the animals in excellent health, well cared for, and most kindly treated, and I have seen nothing to indicate that any of these ponies had a grievance. The inexperienced sightseer may make his way along one of the main roads expecting to come upon a large space with a crowd of miners altogether clearing it of coal, but such expectations will not be fulfilled, for he will find nothing but a series of roads or tunnels. When the visitor gets away from the main road, he finds he can no longer stand upright, but has to walk along with his body bent at right angles, and even then his guide will warn him occasionally to watch his head, or to be careful not to touch the roof at some particular place, as it is just hanging. As he walks along, guided by the light of a small lamp, the visitor notices some cables hung up in a very temporary fashion on the walls of the road or from the roof, and he learns that these are conveying electricity to the coal-cutting machines. He need not ask why the cables are so loosely tied up, for he soon comes upon a fall, where the roof has come down and almost blocked the whole road, leaving the visitor to climb through a space that is only entitled to be called a hole. Here the cables have come down with the roof, but being slack and only insecurely fastened, they have offered no resistance to the fall, so that no damage has been done. The fall will soon be cleared away, and wooden props put in to secure the roof. In some mines where there are bad roofs, one finds in these roads whole regiments of wooden props, which continually require renewal, as they give way under the great pressure. From this side road, which the visitor has been walking along, there are a dozen narrow passages branching off at right angles to it, but there is no sign of coal cutting yet. These 12 roads, about 16 yards apart, lead up to the coal seam. This seam, which could originally be seen along the wall of the side road, has had a number of slices cut off its whole length, and as each slice was taken out, the cavity was filled in, with stone rubbish taken from these passages, their roofs being cut away to give the miners room to draw in the hutches or trucks and get the coal away. The visitor enters one of these 12 passages, being informed that he is in road number 8, and as this seam has been worked for some time, he finds he has quite a long way to travel in a very cramped position, for it is difficult to avoid touching the roof with his back. On reaching the end of this road, he comes to what at first appears to be a dead end, and as he has come during the night time in order to see the electrical coal cutters at work, he finds no one in this road at all. He soon hears the hum of machinery in the distance, and on taking his lamp to the apparent dead end, he finds a narrow passage only 18 inches in height and 4 feet wide, running right past the end of his road. If the visitor cares to crawl or worm his way along this narrow passage, he will soon come on the end of number 7 road, and then a little further on the end of number 6 road, and so on, all these roads leading up to the face of this same seam. But as the noise of machinery is drawing nearer, and as everywhere it is pitch dark, he prefers to crawl back to the entrance of his road. Very soon he hears 2 men calling to each other occasionally over the hum of the machinery, and in a little he discerns a miner coming creeping along this narrow passage with a pick and shovel, clearing the way for the electric coal cutter. It is no easy task to use a pick and shovel while lying flat down with only 18 inches between the floor and the roof, just about the space below an ordinary chair seat. Close behind this man comes the coal-cutting machine, sliding along on skids, and as the machine practically fills the whole space, the visitor cannot get a view of it till it comes opposite the end of his road. It is in this position that the accompanying photograph was taken. When the machine comes within sight and passes the end of his road, the visitor finds it is drawing itself along by means of a haulage rope, which is fixed at some distance along the passage, and is being gradually wound onto a drum in the machine. The machine, which is about 8 feet long, is followed by another miner, who is controlling the working of it. From one side of the machine extends a long arm or drill fitted with small points or picks, and this arm or bar has both a rotary motion and a to and fro or saw-like motion at the same time. The bar or cutter is put into any desired position, and may be arranged to cut away the fireclay below the coal seam, or if, instead of fireclay, there is very hard rock or pavement beneath the coal, the cutter bar can be adjusted to cut along the top of the seam. This particular seam, which the visitor is watching, is being undercut, and what the machine really does is to cut away the foundation from the coal, the bar going in 3.5 feet or even further. The coal cutter travels along the existing face of the coal seam, cutting away the foundation and leaving a space of less than 5 inches in height for 3.5 feet in under the seam, and in one night this machine, requiring only the attention of 2 men, will cut from 100 to 150 yards in length. Of course, the rate of progress is very dependent upon the space in which the miners have to manipulate the machine, for as new picks have to be put in several times during the night, this operation will take much longer if the miner has to do it while lying on his face, side or back. In a deeper seam, the miner can use his tools more easily, and the largest cut of which I have any direct evidence is one in a 3-feet seam, where a length of 200 yards was undercut to a width of 5.5 feet in 10 hours' time, for 6 hours only of which the machine was actually working, which means a speed of more than 1.5 feet per minute. The nature of the soil underlying the coal also determines the speed of the machine, and consequently the distance cut per night. When the coal-cutting machine has cut away the foundation from the coal, it has done the hardest part of the work. One can imagine a miner having to cut away the foundation of an 18-inch seam by hand while lying down. He would probably do 5 yards by the time the machine had done 150 yards, but it would never pay him nor his master, so that narrow seams were formerly left in the earth. They are now being worked out by these electric coal cutters. The seam having been undercut by the machine, it only remains to bring the coal down. It may be that gravity has already brought it down during the night, but if not, the fireman will in the morning drill a few holes in the seam and blast it down, so that it only remains for the collier to clear away the coals, fill his hutches, and leave the seam clear at the end of the day for the machine to work in during the night. As already explained, the cavity between the roads is filled up each day with stone rubbish. That is to say, the whole space formerly occupied by the slice of coal that has been removed is now filled in with rubbish, leaving only the continuation of these branch roads through it. When the slice is cut away, the stone rubbish is not, of course, built in close up to the seam, for sufficient room must be left to let the electric coal cutter work right along the face. If the visitor now creeps along the face of the coal seam, he finds himself in a passage about 4 feet wide, but only 18 inches from floor to roof, and as he goes along he passes the ends of these branch roads, any of which will lead him down to the main road. While I say that the electric coal cutter has done the hard work, I do not mean to belittle the remaining work of the collier, for it is no light task to work in a narrow underground tunnel all day. Again, one has to remember that whereas the collier formerly sent up about 2 tons of coal per day, he has now to send up 4 or 5 tons of the coal cut by these electrical machines. He cannot expect to be paid the same price per ton as formerly, as his master has expended money in cutting the coal for him by the electrical machines, but his wage remains as good as before. Some people will picture the paying off of a large number of miners whenever these labour-saving appliances are introduced into a mine, but on putting this question to the manager of the Holy Town Collieries, Scotland, I learned that this was not the case. The output of the pits is greatly increased, and a fourth pit has been opened at this particular colliery, affording full employment for all their hands. Some idea is given of the work underground by the accompanying photograph. It is curious to watch two men entering what is little more than a crack in the earth, and taking with them a powerful machine, which is receiving power from the surface by means of an electric cable. The taking of this photograph was by no means an easy task, not only because of the very confined space in which to produce sufficient light, but also owing to the intensely black surroundings. I am indebted to Mr. Diesner of Glasgow for his kind assistance in securing what at first seemed an impossible picture, and also to Mr. Stewart of Pollokshaws for aiding me in making preliminary experiments. In view of the report of the Royal Commission on Coal, 1905, it is interesting to note that old mines are now being reopened, and narrow seams that formerly could not be worked are now being cut, at a profit, by electrical machinery. End of chapter 26.
Chapter 27 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 27. Electricity as a Heating Agent. What Sir Humphrey Davy discovered. Arrival of the electric furnace. The greatest temperature produced on the earth. The industrial electric furnace. Electric welding, etc. Electric heating in the home. A new industry. When Sir Humphrey Davy produced an electric arch or arc between two carbon points, he was greatly impressed with the immense heat produced, and he wrote, "Platinum is melted as readily as wax in the flame of a candle." The temperature of the arc itself, that is, say, of the bridge of carbon vapor between the carbon points, is somewhere about 3000 degrees centigrade, or 5432 degrees on Fahrenheit scale. The idea of constructing an electric furnace was a natural result of Davy's discovery. An electric furnace is simply an electric arc with suitable means for enclosing the heat and preventing its escape. It has been found possible, by using special means for conserving the heat, such as lining the furnace with blocks of pure carbon and encasing it in some very refractory substance, to bring the temperature up to 4000 degrees centigrade, which is 7232 degrees Fahrenheit. In the industrial electric furnace it is quite easy to obtain temperatures from 2000 to 3500 degrees centigrade, or 3632 to 6332 degrees Fahrenheit. To assist in realizing what an intense heat this means, it may be stated that cast iron melts at 1100 degrees centigrade, or 2012 degrees Fahrenheit, and from particulars already given, it will be seen that it is possible in the electric furnace to reach a temperature nearly 4 times as great. Some electric furnaces may be arranged to deflect the heat to any particular point, as is done in an ordinary blowpipe. This result is obtained by using an electromagnet to act upon the arc, which behaves exactly as a conductor carrying an electric current, and thus having a magnetic field, it can be repelled by a magnet of similar polarity. There are many devices for regulating the arc, but the general principle of the furnace is understood from the ordinary electric arc lamp, and the simpler an electric furnace is the better in practice, as all its parts are subjected to an intense heat. There is another class of electric furnace on the same principle as that employed in the ordinary electric glow lamp, in which lamp a carbon filament is heated by the current. In this furnace a current is passed through a resisting core, which, being usually composed of carbon, either granular or in rods, offers a very great resistance to the current, and is raised to an intense heat. Such furnaces are termed resistance furnaces, and in some of these the material to be heated or melted is used as part of the conducting core. The expense of obtaining a great heat from electricity is very considerable, for only a very small proportion of the energy used in generating the current appears as heat. It is obvious that under present conditions the electric furnace will not replace the much more economical blast furnace, etc., But under circumstances where a fuel is not easily obtainable, and where water power is abundant, the electric furnace is a very convenient means of converting the energy of the waterfall into heat. The chief use of the electric furnace is to obtain very high temperatures beyond any other known means in practice. There is a third kind of electric furnace, which will be better understood from the chapter on electricity and chemistry, as it is the chemical action of the current upon the materials that is made use of, while the substance is kept in a heated condition. These are known as electrolytic furnaces, and it is this class of furnace that has made aluminum a marketable metal. Where an intense heat is required at any particular point, such as in welding boiler plates, etc., the electric arc is very convenient, as it may be taken to any part of the boiler, one of the wires from the dynamo being fastened to the boiler plate, while the other is fixed to a portable insulating holder. As soon as the carbon is made to touch the plate, and is then withdrawn about a quarter of an inch, an arc is formed, and an intense heat produced. There are many different uses to which electric heating may be put, and among the latest is a small furnace by which dentists may fuse a very refractory substance as a filling in teeth. The dentist may also use electricity for heating air to be blown upon a tooth for drying purposes, thus obtaining a stream of air at constant temperature. It is quite possible to cook food by means of electricity, but it is at present an expensive luxury. It is very convenient to be able to switch on the current to a kettle on the breakfast table and reboil the water for those foolish young friends who think life is so long that they can afford to spend nearly the half of their time upon earth in their beds. It is very nice, especially in summer time, to let the laundry maid do her ironing without requiring a roasting fire, by simply heating some highly resisting wires in the heating iron by passing a current of electricity through them. The cook finds it an advantage to switch on the heat to her range without bothering about the laying of a fire. The whole house may be very comfortably warmed by electricity, and even bed quilts heated by fine wires inside have been made, whether with or without the knowledge of the fire insurance companies I cannot say, but these are certainly luxuries for those who, fortunately or otherwise, do not require to keep an eye on the amount of their household expenditure. In connection with the electric furnace, it may be mentioned that within the last few years there has sprung up a new industry in the manufacture of peat coal. The peat is carbonized in an electric resistance furnace, and may be produced at about 5 shillings per ton. Among other uses of the electric furnace, the most prominent are the manufacture of glass and phosphorus, and the production of carbide of calcium, which is required for the making of acetylene gas. End of chapter 27.
Chapter 28 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 28. Electricity's Relation to Heat. Our fickle sense of heat. Early ideas about heat. Different origins of heat. Heat produces electricity, and electricity produces heat. A thermometer so sensitive that it will measure to the 1/1,000,000th part of a degree. How it is possible to measure temperature up to thousands of degrees. A telltale instrument that reports any carelessness in furnace stoking, etc. A simple experiment shows a very close connection between heat and electricity. What our great-grandchildren will think of our, quote, up-to-date, end quote, methods. The increasing need of specialists. Some remarks about ether waves. Our sensations of heat are merely comparative. It is amusing sometimes, on going out of doors in the morning, to note the different opinions as to the prevailing temperature. One is sometimes greeted with the remark that it is a cold morning, while within a short distance someone else remarks that it is a mild morning. People compare the temperature with the condition of their own bodies, and if one person steps out of the cold air into a warm room, he may say the latter is much overheated, while the occupant finds it just comfortable. This is very forcefully demonstrated by the simple experiment of taking 3 basins of water, having the center one filled with tepid water, and one of the others with very hot water, while the third has very cold water. Keeping the one hand in the hot water and the other hand in the cold water till they become accustomed to their respective temperatures, then plunging both hands into the tepid water. The hand from the hot water complains of the coldness of the tepid water, while the hand from the cold basin feels the same water warm. A youngster would consider his bath quite warm enough, and possibly too warm, at 100 degrees Fahrenheit, while a complaint would be made that his porridge or tea at the same temperature was too cold. It is clear, therefore, that we cannot depend upon our own sensations. We must pay attention to the effects and origin of heat in other things. Electricity has proved a most useful assistant in the investigation of high temperatures, as will be shown at the close of this chapter, but this is not the main relationship indicated in the title used for the present chapter. The early scientists believed heat to be some subtle material substance which could be expelled from one body and taken up by another, but we now know that heat, as reaching us from the sun, is merely an ether disturbance, which, falling upon the material things of this globe, including our atmosphere, sets the molecules into rapid vibratory motion, and that this vibratory movement may be increased to a point at which the molecules can no longer hold together, so that a solid, by the application of heat, becomes a liquid, and in turn a liquid becomes gaseous. We also use the word heat to signify this molecular vibration in a body. Traveling in an opposite direction, we find that a compound gas, such as air, or a simple gas, such as hydrogen or oxygen, will, when the vibratory motion called heat is reduced, become liquid, and when a sufficiently low temperature is produced, liquid air may even become frozen or solid. And if it were possible to reach a point of absolute zero, at which there would be no vibratory motion, the molecules would doubtless fall to pieces. Following this line of thought, one is tempted to wonder whether, if it were possible to rob the atoms of all internal motion, they would not cease to be matter and become part of the great ether ocean. We have a mechanical origin of heat, as is forcibly exhibited when a steam hammer, by repeated blows, raises a piece of iron to a red heat. There is also a chemical origin of heat, as daily demonstrated in our fireplaces by the chemical changes we call combustion. But what concerns us most in this chapter is that there is an electrical origin of heat as is exhibited in an electric lamp, or indeed in any conductor carrying an electric current. In addition to these, there is a radiative origin, as already indicated by reference to the sun sending out ether waves, which produce molecular movement in matter. We have seen in a former chapter that while electricity may produce magnetism, the converse is also true, for magnetism produces electricity. In the dynamo, we found mechanical motion producing electricity, while in the motor, we saw electricity transformed to mechanical motion. In a similar way, while electricity produces heat, it is likewise true that heat produces electricity. In the 20s of last century, Professor Seebeck of Berlin was experimenting with simple couples of metals and thereby studying the volta contact theory referred to in Chapter 3, when he observed that if the point of contact of any two metals was heated, a constant current of electricity was set up in the connecting wire. This was easily demonstrated by placing a pivoted magnetic needle to act as a detector of current upon a block of metal bismuth and forming an arch of copper over the needle, the copper being joined to the bismuth at the two ends of the block. When a lamp was placed at one of the junctions of the metals, the magnetic needle turned outwards, indicating a current of electricity flowing in the neighboring metals, just as the needle telegraph replies to the current in its surrounding coil. In this way, it was found that if any two dissimilar metals were joined together, and the junction heated, there would be a flow of electricity in a wire joining the two extremities of the metals together, provided these were kept at a lower temperature than the junction. Electricity produced by such means is termed thermoelectricity, the name merely indicating its source. People set about making batteries, or, quote, piles, end quote, of these couples, but the electromotive force of such a thermocouple was found to be very small when compared with that of an ordinary voltaic cell. Bismuth and antimony are the metals usually employed for experimental thermocouples, but these are of chief interest to the scientist. One practical application of the thermocouple is in obtaining very exact measurements of differences of temperature, one invention being capable of detecting a difference of less than 1/1,000,000th part of a degree. Of course, an instrument of such delicacy is not required in everyday life, but it is useful in a scientific laboratory. It is very important, however, in the industrial world that we should have means of reading very high temperatures, such as the heat of a blast furnace or a pottery kiln, and for such purposes a thermocouple comes in as a very useful servant. If a thermocouple, protected in a fireproof porcelain tube, be inserted in the source of heat, the temperature of which is desired to be known, there will be a current of electricity passing out along the connecting wires, and this current will be in proportion to the amount of heat producing it. So all we now require is a delicate galvanometer, which is a magnet capable of turning in a surrounding coil of wire to indicate the presence and the amount of the current. The more the current that passes, the farther will the magnet be turned round, so that a scale may be marked off representing heat degrees, and so arranged that the magnet will point out the temperature corresponding to the current set up by that particular degree of heat. Such instruments are generally called pyrometers, and are capable of reading temperatures as high as 3,000 degrees Fahrenheit. They may be made to read any temperature, provided the thermocouple is able to withstand the heat. Pyrometers may be made to record the variations of these high temperatures, and one can imagine these little telltale recorders locked up all night in the darkness of the manager's private office, but truthfully informing him in the morning of any carelessness or irregularity on the part of those whose duty it is to keep the furnaces, etc., at a constant temperature. The electromagnetic effect of the coil upon the magnet is so very small that much skill is required in the making of these instruments, and I have seen a difficulty arise from such a small cause as a trace of iron being in the brass of a very small screw, which being carried by the indicator affected its behavior towards the thermocurrent. A well-made pyrometer is quite reliable, and this is a use of thermoelectricity, which, no doubt, will be valued more as our industries advance along more scientific lines. Although thermobatteries have been used in France for working telegraphs, and even for lighting glow lamps on a small scale, their present use is as a sensitive measurer of very slight differences of temperature, and as an indicator of extreme heat or cold. It would be folly to think that scientists have already got to the, quote, end of things, end quote, as regards the most economical method of obtaining electric currents. Ultimately, man may find a means of dispensing with the clumsy method of converting heat into mechanical energy by means of the steam engine, which is done at an enormous loss. For it is a remarkable fact that the very best steam engines of our time can only give us about 12% of the energy in coal. Our great-grandchildren will doubtless consider our, quote, up-to-date, end quote, methods very crude, for with the steady advance of scientific knowledge, there is bound to be an equivalent advance in the industrial world. The short time we are upon this earth does not give us opportunity to explore thoroughly more than a few of the main paths of knowledge, or possibly only a single main road and some of its side lanes or ramifications, so that as the accumulation of knowledge goes on at a quickly increasing rate, the need of specialists will become even much more marked than is the case at present. In closing this chapter, it may be remarked that although heat waves in the ether were, until quite recently, believed to be entirely different in character from light waves and actinic or chemical waves, the distinction is fast disappearing, and the tendency is to consider all these ether waves as light waves, whether affecting the vision or not, and it is in this connection that a new word is required to save confusion with the word light as used to denote a sensation. It is now becoming more common to speak of heat as the phenomenon exhibited in matter, and to call the heat waves in the ether, quote, radiant energy, end quote. All ether waves are set up by the vibratory movement of molecules and atoms of matter. As already indicated, the molecular energy in the sun disturbs the all-pervading ether, which again sets up molecular motion in matter, and so on. The connecting link between matter and the ether will be explained when we come to consider what we know about electricity. End of chapter 28.
Chapter 29 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 29. How Electricity Aids the Conjurer. A Spirit Seance. A most remarkable borrowed penny. How the audience are led astray. A wizard of 60 years ago. An extraordinary mansion. Electricity is a very helpful assistant in enabling the conjurer to delude his audience. There is no mystery now in a drum beating while suspended in the air, or in musical instruments playing in inaccessible parts of a hall, as the public have become well versed in the electrical transmission of power. But a very good representation of a spirit-rapping seance may be given by similar means. It is not my intention to attempt to expose the methods of any public entertainer, but on several occasions I have concocted and performed some electrical magic for the amusement at entertainments given in behalf of charities, and I shall use some of these as illustrations of how electricity aids the conjurer. In order to give an imitation of a spirit seance, one may place an empty tin box upon a little table at the front of the stage, and then, calling on the ethereal spirit to come and make itself manifest, make the audience hear, above the soft musical refrain from the piano, a distinct series of raps. First of all in some inaccessible corner, and then coming gradually nearer the stage till the rapping is distinctly heard upon the table, and ultimately upon the empty tin box, which has been previously examined by one or more of the members of the audience, and placed by one of them upon the table. If one of the audience now selects any card from a pack of playing cards, the spirit will tell the number of the card, and when asked to answer by a single rap whether the card belongs to hearts, clubs, diamonds, or spades, it will remain silent till the right suit is named, and the conjurer is able to assure the audience that he did not know what card had been selected until he heard the raps from the empty box. A good deal of amusement can be obtained by such imitations, and there can be little secret here to disclose, for it is evident that the raps are produced by hidden electromagnetic devices, similar in principle to an ordinary single-stroke bell. The raps on the empty tin box are really taking place on a long, flat tin box concealed under the tabletop. And all these devices, placed in different parts of the room, are under the control of an assistant behind the scenes. The rest is mere trickery, as, for instance, with the cards. The conjurer has one complete pack of playing cards, and in addition, many packs of the same appearance, but each of these consisting of 52 cards of one particular value, the ace of spades, the 10 of diamonds, and so on. The Conjurer, of course, merely exhibits the complete and honest pack, and while he is asking a member of the audience to select any card, he exchanges the pack for one of the faked ones. In order that he may say to the audience that he does not know the selected card, he simply picks up at random any one of the faked packs before going on the stage and, without looking at it himself, he hands the hidden confederate one of the cards, so that this assistant controlling the electric switches will now be able to cause the tin box to rap out the number and suit of the card, which will necessarily be selected by the audience. This seance may, of course, be extended in a great variety of ways. To take as another illustration, a trick which I recently invented, and which met with the approval of a large audience. Coming upon the stage, I placed 2 small tables in the front, one at either end of the platform. I then request the temporary loan of 1 penny, which is easily obtained, but so that there may be no misunderstanding, I ask the lender if he will be good enough to mark the penny with his knife in any way he desires, so that he will not fail to recognize it again. This having been done behind my back, I request a lady close at hand to seal the penny up in an envelope and retain it meantime. Going upon the stage, I exhibit an empty tin box, and assuring the audience that it is empty, and contains no hidden machinery of any kind, I request that anyone desiring to examine the box for himself should do so. A gentleman comes forward, but as soon as the box is touched, it deals out a series of sudden shocks, so that the examiner refuses to have anything more to do with it, and no one else seems willing to risk electrocution, while the convulsive jumps of the would-be inspector have given the audience and himself some amusement. Remarking to the audience that I suffer no inconvenience in handling the box, I proceed to close it, not only putting its lid on, but also tying a ribbon around it to ensure the lid remaining firmly closed. Holding the box by the ribbon, I place it upon 4 glass tumblers, which act as transparent legs to keep the box clear of the table and insulated from the rest of the material world. Now, taking a pasteboard box down to the audience, I request the lady, who has meantime held the borrowed penny, to place it and its enclosing envelope inside the box, she tying a ribbon around it to prevent my opening it. Carrying this box by the ribbon and keeping it in view of the audience all the time, I place it upon 4 other glass tumblers on the little table at the opposite end of the stage from the tin box. Then, standing right in the center of the stage, I tell the audience that the borrowed penny is now in the pasteboard box, securely sealed up in the envelope, just exactly as the lady placed it there. It may be remarked here that some people think that a conjurer has a special license to say a thing is somewhere when it is not, but that is never the case. He may pretend to place something where he really does not, but when he tells the audience that the borrowed article is in a certain place, then it really is there. Thus assuring the audience that the borrowed penny is still in the pasteboard box, I ask them to pay particular attention to my movements, watching that I never go near either of the tables. I then command that the penny should break up into its individual molecules, so that it may easily pass through its imprisonment. A little gentle music from the pianist, and I inform the audience that if they can see a sort of mist hanging over the stage, they can then see the penny in solution. I then command that the penny shall, after a few bars of lively music, quickly rush together again and fall down inside of one of the 4 tumblers under the tin box on the other table. At the moment when the music ceases, the penny is distinctly heard to fall into one of the tumblers, but not satisfied with this, and still standing in the center of the stage, I ask the penny to once more quickly disintegrate and pass through into the tin box. A few bars of music in the audience, listening to the movement of the penny, are satisfied that it has entered the box. But to show how well under control it is, I ask the penny to spin round on the bottom of the box. This is done, and still remaining in the center of the stage, I request the gentleman who was good enough to lend me the penny to come up on the stage himself and open the tin box, and I ask him to tell the audience quite frankly whether or not it is his penny that is now in the tin box, and I assure the gentleman that if he finds the marks as he made them, he may be certain that there is no trickery there, as I have not the faintest idea how he marked the coin, nor has any confederate seen or handled it. Having removed the ribbon and the lid, the lender carefully examines the penny, which he emphatically declares to be the borrowed penny and no other. I then ask the gentleman if he will be good enough to lift the pasteboard box off the other table and take it down to the lady who deposited the penny in it. She finds the envelope empty, but without any trace to indicate how the penny escaped. More than one scientific friend remarked to me after the performance that if it was really true that the borrowed penny was still in the pasteboard box after I left it on the table, it seemed an utter impossibility that the lender should find it in the tin box. I not only assured them that the penny was left in the pasteboard box, but it was also true that I never handled the borrowed coin after handing it over to the lady for sealing up in the envelope. All this, doubtless, seems mysterious, and yet it is very simple from behind the scenes, for it is very much easier to make up an entanglement of this kind than it is for an outsider to disentangle it. First of all, the electrical apparatus is very simple and is merely to deceive the sense of hearing, upon which the audience are going to depend as to the whereabouts of the borrowed penny. I first of all made up a flat glass vessel to be placed immediately under the tabletop, and I supported a penny over this glass box by drilling a hole in the coin and passing a fine silver wire through it over the top of the box. The silver wire was connected to the wires leading down to the legs of the table, and thence under the carpet to the back of the stage, where an assistant would switch on an electric current and fuse the fine silver wire, allowing the penny to fall into the glass vessel at the desired moment. This jingling noise of the falling penny really takes place, of course, in the glass vessel immediately under the tabletop, but the audience believe it to occur in the tumbler. A similar stretch wire and penny placed over a hidden tin box completes the deception as far as the dropping of the penny is concerned. Another tin box with a simple electromagnetic device sets a penny spinning on the bottom of a box. The audience hears these sounds while intently watching the box and tumblers on the top of the table, and the deception is wonderfully efficient. While the conjurer here depends on electricity to produce the desired effect as far as the senses are concerned, there must be an attempt to mystify the mind or to lead the thoughts of the audience astray. The most misleading part of the trick really consists in my being able to deceive the audience as to the identity of the borrowed penny. To make the matter quite clear, let us first of all merely follow the borrowed penny. I took it from the gentleman, handed it to the lady, who sealed it in an envelope, and later on placed it in the pasteboard box. The box was taken onto the stage, the penny was never touched, and still lay there where it was put till the trick was over and done, and the audience away. I made the box with a false bottom so arranged that it at first acted as one of the sides, being folded back against the real side, and I had previously placed an empty envelope, identical in appearance to the one I gave to the lady, between the false bottom and the side, so that when the lady deposited the envelope with the borrowed penny in the box, the false bottom closed down upon it, safely hiding it and exposing in its place the empty envelope, to be discovered there later on. This was the borrowed penny, but it was not the penny the lender marked, for when he handed me the penny at the outset, I pretended just to recollect, as I was taking it from him, that it would be better to mark it, whereas I really handed him another penny of my own, which I had hidden in the palm of my hand. He took this penny, believing it to be the penny he had just taken out of his pocket, and if questioned I doubt he would admit that the penny ever left his hand, and so he marked this penny of mine. I retained this marked penny, leaving the borrowed penny with the lady, and while the audience were laughing at the eccentricities of the gentleman who got a shock on touching the tin box, I placed this marked penny on the bottom of the tin box, then put the lid on and tied it up. The trick was, of course, really over as far as I was concerned, before it had begun in the minds of the audience, and this is a safe principle upon which to build up a trick. I was able to say truthfully that the borrowed penny was in the pasteboard box, and it was the lender who examined the marked penny in the tin box and said that it was his penny. It certainly was the penny he marked, but not the borrowed penny, and so the mystery was obtained. In order to deal out the electric shocks from the tin box to the would-be inspector, I had previously deposited 2 large pieces of sheet iron below the carpet and connected these to a battery and induction coil under the control of an assistant behind the scenes. When I stood on one hidden plate and the member of the audience over the other plate, we completed the circuit through the box in our hands. Of course, I received a similar shock to the victim, but Being prepared for it, I took it more calmly. This part of the trick was merely a blind to give the amateur conjurer a safe opportunity of placing the marked penny in the box without attracting attention. One would hardly credit how much the audience really see in their imagination. I have heard the narration of some of my tricks by members of the audience, and it is really quite remarkable how the actual facts are altered by their imaginative powers. This somewhat lengthy description will serve to illustrate the application of electricity to the black art. A very interesting account was published about a quarter of a century ago of how Robert Houdin, a famous French conjurer, amused himself after his retirement to a beautiful mansion in the village of Saint Gervais. For this account, I've extracted those parts seeming of most interest. In describing the mansion, the writer, presumably Houdin himself, says with reference to the avenue gateway, distant about a quarter of a mile from the house, "The visitor, presenting himself before the door on the left, sees a gilt plate bearing the name of Robert Houdin, below which is a small gilt knocker. He raises this according to his fancy, but, no matter how feeble the blow, a delicately timed chime of bells sounding through the mansion announces his presence. When the attendant touches a button placed in the hall, the chime ceases, the bolt at the entrance is thrown back, the name of Robert Houdin disappears from the door, and in its place appears the word Entrée in white enamel. The visitor pushes open the door and enters. It closes with a spring behind him, and he cannot depart without permission." This door and opening sounds two distinct chimes, which are repeated in the inverse order in closing. 4 distinct sounds, then, separated by equal intervals, are produced. In this way a single visitor is announced. If many come together, as each holds the door open for the next, the intervals between the first 2 and the last 2 strokes indicate with great accuracy, especially to a practiced ear, the number who have entered, and the preparation for the reception is made accordingly. A resident of the place is readily distinguished, for, knowing in advance what is to occur, he knocks, and at the instant that the bolt slips back, he enters. The equidistant strokes follow immediately the pressing of the button. But a new visitor, surprised at the appearance of the word Entrée, hesitates for a second or 2, then presses open the door gradually and enters slowly. The 4 strokes now indicated by a short interval succeed the pressing of the button by quite an appreciable time, and the host makes ready to receive a stranger. The traveling beggar, fearful of committing some indiscretion, raises timidly the knocker. He hesitates to enter, and when he does, it is only with great slowness and caution. This the chimes unerringly announce. It seems to persons at the house as if they actually saw the poor mendicant pass the entrance, and in going to meet him they are never mistaken. Electrical arrangements were also provided for signaling the arrival of a carriage and dealing with the gates in response, while a postman received from a bell at the gate instructions whether to leave the letters in the box, or if it was necessary for him to go up to the house to collect some letters. "My electric doorkeeper," says Houdin, "leaves me nothing to be desired. His service is most exact, his fidelity is thoroughly proven, his discretion is unequaled, and as to his salary, I doubt the possibility of obtaining an equal service for a smaller remuneration." Houdin had a favorite mare to which he was much attached, and the food for this horse was automatically placed in its trough thrice daily, the apparatus being controlled by a clock in the study. The reason for this arrangement seems to have been that Houdin had found his mare being underfed by a former hostler who converted as much food as possible into hard cash for his own behoof. In order to prevent the hostler remaining in the stable while the horse was fed, the oats were only allowed to fall into the trough while the stable door was shut and locked, and he could not remain in, as he could only lock the door from the outside. The man could not re-enter while the oats were in the manger without his master being informed of the fact, for if the door was opened before the oats were finished, a signal was given in the house. The power for ringing some bells in the tower was stored in a most ingenious way, for between the kitchen situated on the ground floor and the clockwork in the garret, there was a contrivance so arranged that the servants, in going to and fro about their work, wound up the weights without being conscious of it. The ringing of these bells was electrically controlled by the study clock, which also operated time dials in several rooms. If Udon desired dinner earlier, he simply pressed a button in the study and put the kitchen clock forward a quarter of an hour. The same clock switched on continuous ringing alarms to waken the servants in the morning. Udon evidently had his greenhouses connected with his study by thermoelectric apparatus, for he would surprise his gardener by saying, "Jean, you had too much heat last night. You will scorch my geraniums." Or, "Jean, you are in danger of freezing my orange trees." The house was fitted with automatic electric fire alarms and burglar alarms, the latter being switched on to every door and window at the hour of midnight by the study clock, and again disconnected by the clock in the morning. It is probably almost half a century since this wonderful mansion was thus equipped. I have found no means of learning exactly when Udon retired and went to live in it, but it is certain that he was using electromagnetic apparatus to aid him in stage effects in Paris during the year 1845, at which date we consider electricity to have been in its early infancy. End of Chapter 29. Read by Lindsay Strausser. Jacksonville, August 2022.
Chapter 30 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2022. The Romance of Modern Electricity by Charles R. Gibson. Chapter 30. How we measure electricity. Our present primitive methods of measuring material things. No artificial standards in electricity. A most eccentric genius does much to aid electrical progress. How the electrical units were named. An absent-minded philosopher. An explanation of the units. How the pressure and rate of flow are measured. How the consumption is measured. The earliest consumption meter. How a modern electric meter works. A clumsy method of paying for energy, and an exact electrical method. To measure any material thing is an easy matter, for we may compare it with some other known object. One may say that a thing is so many times longer or heavier than a certain other thing, which we agree to take as a standard. Some of the earliest standards used were the finger, the hand, the forearm, cubit, the foot, the span, the stride, the mile of 1,000 paces, and so on. Early in the 14th century, about 10 years after the Battle of Bannockburn, it was agreed that 3 grains of barley, dry and round, do make an inch, and 12 inches make 1 foot. Even now our methods are entirely artificial, although, fortunately, more definite than these primitive standards. It would seem very primitive indeed if our legislators merely made 2 chalk marks on the floor of the House of Commons, and then informed us that the distance between these 2 marks must be reckoned a foot or a yard or any other name they cared to give it. But in point of fact, our present method is really just as primitive, except that we have taken care to preserve the marks for future reference. We have, locked up at the Standards Office in London, a bronze bar 38 inches long, having 2 gold studs sunk into the bar near its ends. On both studs a line is cut, and the distance between these 2 parallel marks is the length we have agreed to call the yard. But in order to be as exact as possible, the measure must be made when the metal bar is at a temperature of 62 degrees Fahrenheit. All other lineal measures are either smaller parts or multiples of this definite but artificial standard. The unit of weight is the pound, and this is defined by a certain piece of platinum, also preserved in the Standards Office. 4 copies of these standards are deposited in other places of safety, in case of any accident. The French have attempted a more natural standard of length, in taking the meter as 1/10,000,000th part of the quadrant of the earth through Paris, but this is not absolutely correct, so that the French have their standards preserved in their capital just as we have. On visiting the Bank of England, one finds that, instead of counting the sovereigns, an official desiring to fill a bag with, say, 1,000 pounds, simply weighs out a certain weight of sovereigns as though he were weighing sugar. This is, of course, a perfectly reliable method, as the scales are very sensitive, and he already knows by experience that 1,000 sovereigns weigh a certain amount, so he is confident that if he gets the weight correct, he will have the number of sovereigns also correct. The number of coins is here arrived at by the weight, or in other words, by the effect of gravity upon the mass of the coins. We measure heat by its expansive effect upon a column of mercury or spirit, or by its electrical effect, as explained in an earlier chapter, and in a similar fashion we measure electricity by its effects. In previous chapters we have noted the magnetic effect produced by a current flowing in a coil of wire, and as the magnetic effect is in proportion to the amount of the controlling current, we have, in this effect, an exact means of measurement, and most electrical measuring instruments are based upon this magnetic effect. If we take a coil of wire and suspend a magnetic needle in it, we find the magnet deflected more and more as the current increases, but the amount of movement will, of course, be also dependent on the size of the coil, the number of its turns, etc. So where are we to find a convenient standard to lock up? It is fortunate we do not require to base our electrical units upon any artificial standard, as we do for our measures of length and weight. When electricity came to be used in everyday life, it was found necessary to have a definite measure to refer to, for it would not do merely to record, as some early experimenters did, that the current required for a certain result was such that it dashed the needle of his largest galvanometer against its stops, and so on. About 40 years ago it became quite evident that a great deal would depend in the practical applications of electricity upon having a proper system of measurements. With this in view, the British Association for the Advancement of Science appointed a committee of scientific men, with Sir William Thomson, Lord Kelvin, as its leading light, to suggest suitable standards of electrical measurement. It is not within the scope of this book to show how these absolute units were arrived at, and indeed, a statement of the facts would not interest those who have not already gained a certain amount of scientific knowledge. But I think it will be of interest to the general reader to know how electricity is measured by these fixed units. We have already seen in Chapter 8 the great amount of money lost in the early submarine cables, which were not capable of doing the work required of them, and the true explanation of this unnecessary waste seems clearly to lie in the fact that at that time there did not exist any proper electrical measurements. It is of interest in passing to note that a great deal of credit, in connection with the basis of electrical measurements, is due to the individual labours of a rather eccentric gentleman, the Honourable Henry Cavendish, a nephew of the 3rd Duke of Devonshire. Cavendish was a great genius, and he contributed much of value to many branches of science. Having plenty of this world's wealth, he used to shut himself up in his laboratory and busy himself day after day experimenting, from a true love of science. He was in the habit of lending books from his library to any man of science known or recommended to him, and in connection with this it is surprising to find that he was so methodical that he never took down a book for his own use without entering it in the lending register. I say that one is surprised to learn of this methodical plan, for it is a known fact that this great genius was very careless in recording his scientific results, often merely jotting them down on the backs of old envelopes or other loose scraps of paper, and though a publication of his researches was made, after a lapse of some 80 years, by Clerk Maxwell, there doubtless must have been many interesting facts never made known. Cavendish was so devoted to his hobby that society had no attractions for him. He only met his heir once a year, he himself being a bachelor, and all his intercourse with the outer world may be summed up in his attendance at the meetings of the Royal Society and dining with its members once a week. Any instructions to his servants he wrote down and left in a note on his hall table, while his maidservants were ordered to keep out of his sight on pain of dismissal. The British Association Committee decided to name the electrical units, agreed upon, after the great men of science who had done so much towards the advancement of the science, and it seems to me a pity that the name of Cavendish was not memorialized in some form, although it is sure to be kept in remembrance by all students of physics. The unit of pressure, or electromotive force, has been called the volt, after Volta, who discovered the flow of electricity between two dissimilar metals in contact, which discovery led to the construction of batteries. The unit of current, or rate of flow, was called the ampere, after the great French scientist of that name, who suggested the galvanometer, and who did much for the science of electricity. This great physicist was said to have been at all times so absorbed in his work that his wife had very great difficulty in getting him out of his laboratory, even when he had some important appointment to keep. The story is told of how on one occasion, when he and Madame Ampere were to attend some great banquet, his wife at last succeeded in getting him away from his experiments and upstairs to dress, but she evidently did not get him away from the problems working in his mind. After waiting impatiently for his arrival downstairs in evening dress, she was at last compelled to go up and ascertain the cause of delay, and one can well imagine her dismay when she found the great genius sound asleep in bed. His mind had been so absorbed that, coming away with the intention of preparing to don his dress suit, he automatically went to bed, and having doubtless arrived at a satisfactory solution to the absorbing problem, fell into a pleasant slumber. The unit of electrical resistance was called the ohm, after the great German physicist, Professor Ohm, who formulated the law that the strength of an electric current in a wire depends not only upon the electrical pressure driving it through the wire, but also upon the amount of resistance offered by the wire to the passage of the current. While we are not to think of this resistance as a mechanical friction, yet it is well to fix in our minds that this resistance is an inherent property of the conductor itself, and not in any way dependent upon the current that happens to be flowing through it. These three units, the volt for pressure or electromotive force, the ampere for the rate of flow, and the ohm for resistance, are the three practical units of most common use. We all have a fair estimate of what a yard or a pound is, and it would be well if we also formed some conception of what these electrical units are like. Some idea of the magnitude of a volt may be obtained from the statement that the electric pressure, or electromotive force, of a single battery cell is between 1 and 2 volts. In thinking of the ampere, we must remember that it is the unit of flow in 1 second of time, just as one would say of water, so many gallons per minute. It is in amperes we measure the current, while the volts merely indicate the pressure at which the current is supplied. We may think of an ampere as being the current required to make an ordinary glow lamp bright, but this may vary from 1/3 of an ampere to 3 amperes, according to the thickness of the carbon filament which the current has to heat. In an arc lamp we require a rate of flow of from 10 to 20 amperes. Thus, the heating of a wire or other conductor depends on the number of amperes passing through it, while the voltage will be determined by the resistance we have to send the current through. The pressure required to work an arc lamp, with the great resistance offered by the air space between its carbon points, is seldom less than 60 volts, whereas a small glow lamp, with its continuous filament, may be worked with as low an electromotive force as 3 volts. It only remains to form some conception of the ohm or unit of electrical resistance. The value of the practical ohm is very conveniently arranged so that it requires a pressure of 1 volt to send a current of 1 ampere through the resistance of 1 ohm. Here we have a very convenient relationship between the volt, the ampere, and the ohm, for if we know the value of any two of these, the third may easily be found. If we have a circuit of 2 ohms resistance and we have a source of supply at 6 volts pressure, then we know that the rate of flow will be 3 amperes, for each volt will cause 1 ampere to flow through 1 ohm, so that the 6 volts would give 6 amperes through 1 ohm, but as the resistance is doubled, that is 2 ohms, then the 6 volts will only get the current to flow at half the rate, that is 3 amperes. We may count the value of the practical ohm to be the resistance of 1/3 of a mile of copper wire, about 1/10 of an inch in diameter, or one may think of a mile of ordinary iron telegraph wire as having a resistance of 13 ohms. It will be clear that we must be able to read both the pressure and the rate of flow, and these are easily indicated by the effect of the current in passing through a coil of wire in which a magnetic needle is pivoted. To measure the pressure we have a voltmeter, which we may consider as analogous to the pressure gauge on a steam boiler, and to measure the rate of flow of current we have an ammeter or ampere meter. Both of these instruments are galvanometers, having a coil of wire with a magnet at its center or some other arrangement based on this principle. In general appearance they are very similar, and one might quite imagine an Irishman saying that if they were not similar, they were the same. In point of fact, the only difference is that the ammeter has a coil made of a short, thick wire so as not to obstruct the rate of flow, and the voltmeter has a long coil of thin wire to offer a great resistance to the current. It seems rather strange that both the pressure and the rate of flow should be independently measured by the effect of the current upon a neighboring magnet. It is difficult to find an adequate analogy, but one's mind naturally thinks of water, and so perhaps the following picture may be of assistance. If we imagine a pipe through which water is flowing at a constant rate, we might place a very little water wheel in its course to indicate, by its revolutions, the rate of flow of the water. Again, if we desired to find its pressure, we might apply a definite friction to the water wheel, so that it would require a certain amount of pressure to turn the wheel at a given rate. This must only serve as a rough analogy, with the water wheel representing the magnet, but one can see, in the first case, the water left as free as possible to turn the wheel, which corresponds to the ammeter with the heavy wire allowing the current to pass freely. Again, in the second case, we put a resistance in the way of the water, and thus measure its pressure against this obstruction, which in some degree is analogous to the voltmeter, in which we place a definite resistance in the form of a long coil of fine wire. It is unnecessary to describe the details of construction of these instruments, as these particulars may easily be understood from the principle just explained. The dial of the ammeter is, of course, marked off in amperes, and the voltmeter in volts. It will naturally be very difficult for anyone to realize merely by reading about volts and amperes what these units really are. One only comes to realize what a pound weight or a yard measure is by repeated use of these units. The meter which will interest the general reader most is the consumption or supply meter. The first current meter was invented by Edison, and many may remember its appearance at the Paris exhibition of 1881. This meter was based on the chemical action produced by a current passing through a solution of copper sulfate. It was, in fact, an electroplating apparatus, having 2 pieces of copper suspended from the opposite ends of a balanced beam. When the current passed from number 1 copper to number 2, it plated the latter with copper taken from the solution and replenished by number 1 copper. As this number 2 copper increased in weight, with the copper plated onto it, it depressed that end of the balanced beam which operated a counting mechanism. When this end of the beam came down a certain distance, It automatically switched the current on in the reverse direction, so that it passed from number 2 copper to number 1 copper, plating the latter this time, which in turn brought the beam down on the other side, seesaw fashion, once more operating the counting mechanism and again reversing the current. In effect, it was simply a means of counting how often the current was able to carry over a certain amount of copper from the one plate to the other alternately, and as the ability of the current to do this depended on the amount of current passing, a direct reading of the current was registered. This gave a starting point for inventors of supply meters, and today forms the basis of some modern meters. Although, in itself, it was not a very efficient meter, owing to its having to work at a variety of temperatures, which affected the conductivity of the liquid. It would not be of sufficient general interest to trace the growth of this class of meter, nor even to describe all the different principles at work. I think it will be enough merely to indicate how the measuring is done in the meters in most common use. Many people are curious to know how an electricity meter works, although they may never bother their heads with the details of a gas or water meter. There is nothing mysterious about these meters to them, for they are operated by substantial matter passing through them, but to talk of measuring electricity seems to them somewhat mystifying. All electric meters, however, are merely means of registering the effect of the current upon certain material arrangements. The most prominent and most useful property of electricity is undoubtedly its effect upon a magnet. We find this property being made use of in dynamos, motors, telegraphs, telephones, etc., and so it is natural that it should also be used as a measure of the current. The more current one supplies to a little motor, the quicker its armature spins around, so that with a delicately adjusted armature, arranged to operate a counting mechanism, we have a reliable current meter, which, of course, more detail of construction than is here mentioned, such as a contrivance for reducing the speed and yet keeping the revolutions proportional to the variations in the current passing through the meter. We ourselves expend a great deal of energy every day in moving about and performing our daily tasks, and we require to lay in a fresh stock of energy, which we do by eating nourishing foods. When we buy food, it is really the energy in the food that is of first importance to us, whether we so consider it or not. Paying for food, however, is a very clumsy method of paying for energy, for we often, wittingly or unwittingly, pay for and consume foodstuffs that add very little energy to our human mechanism, and how often, owing to the hurry-scurry of life, do we fail to extract the available energy from our food. The point I desire to enforce is that while we have here a very roundabout way of paying for energy, we have a very direct and exact method in the electric meter. It is, of course, the energy of the electric current that we desire to measure, and therefore we must have a suitably arranged unit to work with in practice. We have a dynamo giving out a certain current at a certain pressure, according to the construction of the machine, and the speed at which its armature is revolving, so that the energy available will be the quantity of current passing in a given time multiplied by the pressure. The unit for this might be termed a volt-ampere, 1 volt multiplied by 1 ampere, but it is more conveniently called a watt, in honor of James Watt, the inventor of practical steam engines. This unit is too small to be convenient, so electricians have adopted 1000 watts as a commercial unit of power and have named this a kilowatt. It is clear that this is only a measure of the power or capability of the current, and the energy the consumer can get from it depends on how long he can get the use of this amount of power, and so the Board of Trade has arranged that the unit is to be a kilowatt for an hour, sometimes called a kilowatt hour, but better known as a Board of Trade unit, written BTU. If the charge is 6p per BTU, it simply means that the consumer is to get the use of a power equivalent to 1000 watts for 1 hour, and for this he is to pay 6p. Of course, he may spread the using of this kilowatt over any length of time he desires. He may use it at the rate of 100 watts in 1 hour, at which case he may continue using that amount of power for 10 hours, and then he has taken the BTU his meter will have registered, and at the settling of accounts he has to hand over the required money value to the supplier. It is well that the consumer should form some definite conception of what he can get from 1 BTU. A 16-candle power lamp is estimated to consume 60 watts, so that he should be able to have that lamp alight for about 16½ hours at the cost of 1 BTU. It is also well that he should fix in his mind how a BTU is made up, for there often seems to be quite an unnecessary vagueness upon this point. The Board of Trade unit, as already stated, is a power of 1000 watts for 1 hour, 1 watt being 1 volt multiplied by 1 ampere. He may, if he so prefers, remember the BTU as 1000 volt amperes per hour, so that he knows if his current is being supplied at a pressure of 100 volts, then he is consuming 10 amperes in his Board of Trade unit. It may be noted in passing that 1000 watts is approximately equal to 1 1/3 horsepower. Some readers, to whom the subject has been quite new, may still be a little puzzled as to the meaning of the ampere. The other units seem to be more easily grasped than this one, but I think the difficulty arises from an omission to remember that the ampere is not really a measure of quantity, but is a rate of flow, or current strength. The measure of electric quantity is really the coulomb, called after a great French physicist who lived during the French Revolution. A coulomb is the quantity of electricity required to produce a definite chemical effect, to deposit 1.1183 milligrams of silver. An ampere is the rate of flow of a steady current of 1 coulomb per second, just as one may speak of a flow of water being at the rate of 1 gallon per minute. If we had one single word to represent the phrase 1 gallon per minute, then we should have a corresponding word referring to the rate of flow of water, just as we have the single word ampere to represent the rate of flow of electric current. To be told that water is flowing through a pipe at the rate of so many gallons per minute does not indicate the quantity of water that has passed, until one knows for how many minutes or hours the water has been flowing. In a similar manner, if we are given the rate of flow of a current in amperes, we must also know the duration of the flow before we can tell what quantity has passed. A 2 ampere current will have conveyed in 1 hour 7,200 coulombs, which figure is simply calculated as 2 amperes times 60 seconds times 60 minutes. If we have a current strength of only 1/10 ampere, then it will take 10 seconds of flow before 1 coulomb has passed. Speaking of a water wheel, we may say that we require a flow of so many gallons per minute to drive it, and in the same way we may say that we require a current of so many amperes to keep the filament of an electric light glowing. The general reader is constantly coming across the word ampere, but he seldom meets the word coulomb, and it is included in the word ampere, the meaning of which, as already pointed out, is a rate of flow of 1 coulomb per second. It is obvious that if there is a fixed pressure or voltage, one can vary the rate of flow, that is, the amperes, by altering the amount of resistance in the path of the current, just as one does in drawing water off the main through an ordinary stopcock. The further one draws the stopcock out of the pipe, the greater the rate of flow, and the greater resistance one leaves in the path of the water, the smaller is the rate of flow. As already explained, the electrician places coils of various thicknesses of wire in the path of the electric current, and in this way he is able to regulate the current strength. If we wish to maintain the same rate of flow, amperes, through an increased resistance, ohms, then we must increase the pressure, volts. We already saw that it requires 1 volt of pressure to drive a current of 1 ampere strength through a resistance of 1 ohm. It will therefore require a pressure of 2 volts to send the same current through a resistance of 2 ohms. If we had left the pressure at 1 volt and still increased the resistance to 2 ohms, then, of course, the rate of flow would have been only half its original, or half an ampere. While the ampere indicates the rate of flow, it is plain that if a current of 1 ampere be allowed to flow for 1 hour, then we have a definite quantity of electricity, which we term an ampere hour. It requires a certain pressure to send this current through the circuit, dependent upon the resistance offered. If an ampere hour be multiplied by the pressure, volts, then we have the consumption of electrical energy in watt-hours, 1,000 of which are called a board of trade unit. End of chapter 30.
Chapter 31 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Electricity by Charles R. Gibson. Chapter 31. Some Questions Answered. There are a great many points of importance which I have deemed it inadvisable to touch upon in the foregoing chapters, because to many readers these would doubtless seem dry and uninteresting. It is, however, probable that in the minds of some readers there will be a desire for further explanation, and so I have thought it well to devote this chapter to answering such questions as might naturally arise. These few preliminary words will serve to mark this chapter as intended only for the latter. I think the first question would probably be regarding positive and negative electricities, the mention of which has been so scrupulously avoided in the whole of the preceding chapters. These are merely arbitrary terms, but they serve a very useful purpose, and part of the foregoing explanations might possibly have been made simpler by the use of these terms, but my experience has been that, to many people, these and kindred terms are rather a worry, hence my avoidance of them. These terms of positive and negative originated with the one-fluid theory of electricity, in which the plus sign was used to indicate an excess of the supposed fluid, and the minus sign a deficiency, the earth being taken as zero, or we might say as the electrical sea level. These terms have really no connection now with the idea of more and less. We have direct evidence that there are two distinct kinds of electricity. The general reader will be interested in these terms in their connection with electric currents rather than as regards electrified bodies, so I will merely deal with them in the former connection. We form a mental picture of the electric current flowing from the positive pole of a battery or dynamo round the circuit, through the lamps, etc., and back to the negative pole. In a simple battery cell, we speak of the current passing from the carbon connection through the connecting wire to the zinc element, and so we call the carbon the positive pole and the zinc the negative pole. In a dynamo, the position of the poles is according to the direction of winding the coils. It is easy to discover in which direction a current is flowing in a wire by its magnetic influence on a neighboring compass needle. If the wire carrying the current be placed over the compass needle, which is pointing north and south, and when the current passes the needle turns its north pole to the east, then we know the current is flowing in the direction from north to south. Of course, the magnetic needle need not be placed in its natural position as in a compass. It may be mounted on its center in an upright position at the back of a dial, as in a galvanometer, and the indicator on the face moving with the magnet will show its movements falling to one side or the other according to the direction in which the current is sent through the coil surrounding the magnet. It was recognized by some of the earliest workers that there were two distinct kinds of electricity. Later workers departed from this idea. Indeed, it is not so long since some of the foremost scientists of our day thought for a time that electricity was not a real thing, but that electric currents and electric charges were merely phenomena in the ether of space. We have direct evidence now that electricity is a real existing thing. I was very much amused in overhearing some remarks which passed between two gentlemen in a public conveyance. One asked the other how it was that a person might walk along the rails of an electric tramway and yet not receive a shock from the dynamo to which they are connected. His friend's reply was that the rails only carried negative electricity, which was quite harmless, and that it was the positive electricity carried by the trolley wire that killed. This gentleman would doubtless have been surprised if he had been told that a tightrope dancer could walk along the trolley wire with as little fear of electrocution as upon the rails. The space between the overhead wire and the rails is just like a break in the circuit through which the current flows from one brush of the dynamo to the other. When the car comes along, it closes the circuit, allowing the current to flow down the trolley pole through the motor and away back to the dynamo by the rails. If a person gets in contact with the rails and the overhead wire, owing to the falling of the latter, then the person becomes part of the electric circuit and receives a fatal shock. If the person is not on the rails but on the ground, when the overhead wire touches him, he will undoubtedly receive a shock, but the resistance to the current will be so much greater that no very serious injury is likely to be done. The tramway motormen are supplied with rubber gloves with which they may handle a live wire in the event of its coming down. Their duty is to place the end of the wire on one of the rails, whereupon the current is given such an easy path, allowing so great a rush of current that the safety devices at the power station come into action and automatically cut off the current. It may have occurred to some to wonder what amount of current really does kill. Even nowadays, when very occasionally one comes across some elderly lady or gentleman who fears that death may result from an ordinary battery current. I have fallen in with 2 such cases quite recently, but with the widespread use of electricity, such mistaken ideas cannot survive long, even in distant rural districts. Many of us, when youngsters, were informed that birds were often electrocuted by resting on the ordinary telegraph wires. While it is true that a great number of birds are found lying dead immediately below telegraph lines, it is generally known now that their death has been brought about by sudden collision with the wire, against which they have accidentally flown. Hence the little pieces of wood one often sees fastened to telegraph wires in the country are there to attract the attention of the birds to the presence of the wire. From what has already been said regarding the trolley wires, it will be clear that even if a bird were to rest on a live wire, as one sometimes does see on a country road along which a tramway runs, the bird receives no shock, the bird not forming part of an electric circuit. Even now, one often finds some people afraid lest they may receive a fatal shock if handling the connections of an ordinary glow lamp. Of course, this is impossible, and yet one knows that fatal shocks may be received from the conductors for arc lighting. Where, then, is one to draw a distinctive line? The current supplied for domestic lighting is at a low pressure, which cannot possibly do any serious hurt. But it is not entirely a case of pressure, for a person may receive without injury a high-frequency current from an induction coil, etc., with a pressure of many thousands of volts. In the case of high-frequency currents, the amount of electricity is very small. At a pressure of 100,000 volts, the current may only be about 1,000th part of an ampere, although I have seen a medical friend receive as much as 1/200th part of an ampere, or 5 milliamperes. The current that will pass through any body depends upon the resistance it offers, as well as the pressure of the current applied. Fortunately, the resistance of the human body is very high, being estimated at about 10,000 ohms. But if a person grasp 2 metal conductors, the resistance from one hand to the other through the body may only be from 1 to 3,000 ohms. If some vital part of the body offer 1,000 ohms resistance to a current at 500 volts, then half an ampere current will pass through it, and this may be termed a current that kills. I know of a recent case where a workman accidentally touched 2 terminals of a machine receiving current at 500 volts, and he was immediately killed. But in this case there was very little resistance offered to the passage of the current, as the man's head touched both terminals. The current for domestic purposes is supplied at a pressure of about 250 volts, so the human body is a safe resistance against this current. There is no doubt that some of the fatalities from electric shock are really due to the accompanying nervous shock. There were some interesting experiments made recently relative to the conductivity of the human body, and it was found by means of very delicate indicating apparatus that the electrical resistance of the same person was continually varying. It would oscillate even if a third person entered the room during the experiment, and quite a marked difference was obtained by a change of diet. I quote two results which were given in a continental journal, as these seem of interest to the general reader. Quote, "Any sensation or psychical emotion of some strength will reduce instantaneously the resistance of the human body down to a value 3 to 5 times less." Unquote. Quote, "Nervous persons, as well as heavy smokers and drinkers, are found to have an exceedingly low electric resistance." Unquote. The first of these two quotations seems to me to have a definite bearing upon fatal shocks. There is often an alarming display of flashes when a conductor breaks, and in this way the normal resistance of the human body may be very greatly reduced, owing to unusual alarm and nervousness. It is well to know that apparent death from electric shock is sometimes only suspended animation, as is the case in drowning, so that artificial respiration should be tried. One used to hear people laying stress upon the great risk accompanying the use of overhead electric wires in connection with tramway systems. That there is no real cause for alarm, provided proper care is taken, is evident from the experience of Glasgow. This great center of industrial activity adopted the overhead wire system in 1900, and by 1910 there was in use about 190 miles of overhead wire. During all these years, there was not a single fatality caused by the breakdown of an overhead wire. End of Chapter 31.
Chapter 32 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2022. The Romance of Modern Electricity by Charles R. Gibson. Chapter 32. What we know about electricity. What is electricity? Some questions we may answer since the discovery of electrons. What is matter? What is an electric charge? What is an electric current? The difference between a continuous and an alternating current. What is magnetism? The ether of space. What is light? Discovery of a missing link. What is heat? What is chemical union? Importance of the electron theory. Many years ago, I heard one workman explain to another that electricity was made of sulfuric acid and lead. He was evidently aware that accumulators contain lead plates and dilute sulfuric acid, and he knew that electricity was drawn from these accumulators at will. Therefore, it seemed to him as though electricity must be composed of these substances. People sometimes twit the electrician with the question, "What is electricity?" as if his branch of science was very deficient in real knowledge compared with other departments of science. If the questioner is asked, "What is matter?" he will no doubt realize that none of these very simple-looking questions are so easily answered. It will be of interest, however, to see how far we have succeeded in explaining the mysteries of electrical phenomena. Suppose you were asked, "What is water?" You might reply that it is built up of very small particles or molecules of water, each of which is composed of 2 atoms of the gas hydrogen and 1 of oxygen. In the same manner, we believe we may answer the questions, "What is matter?" "What is an electric charge?" "What is an electric current?" "What is magnetism?" "What is light?" "What is heat?" and so on. Some of these questions may seem to have no direct connection with the subject of electricity, but we shall see that a very intimate relationship does exist in each case. When electricity at high tension from an induction coil was passed through a vacuum tube, such as has been described in connection with X-ray work, it was found that a stream of flying particles was shot across the tube from one electrode to the other. At first it was supposed that these flying particles must be atoms of matter, but later it was proved that these particles were not matter. They are far smaller than the invisible atoms of matter. Scientists were forced to the conclusion that these were particles of electricity, and they were christened electrons, after the Greek word for amber. A great deal of attention was directed towards these electrons, which some have preferred to call corpuscles. It was found that those particles of electricity were always of the kind called negative. It will be remembered that from the early days it was evident that there were two distinct kinds of electricity, although it was a single fluid theory that suggested the names positive and negative. We have definite proof that negative electricity is made up of small particles, just as matter is molecular in nature. We have no definite evidence as to the nature of positive electricity, but the discovery of the negative particles has opened up a whole world of new interests to us. We believe the atoms of matter to be composed of little congregations of these electrons. We picture each atom as a miniature solar system, a group of electrons revolving at enormous speeds. Of course, electrons being little particles of negative electricity would all tend to fly away from one another, just as any two similarly electrified bodies will. We therefore picture a counterpart of positive electricity in each atom, but what form it takes we cannot determine. Until recently it was common to picture the electrons revolving within a tiny sphere of positive electricity. Now it seems likely we shall find positive electricity to be molecular in nature also. In other words, that it will turn out to be composed of particles which, although much larger than the negative electrons, are still infinitesimally small. We have always recognized the fact that an atom of gold must be something quite different from an atom of lead or of hydrogen gas. We now believe the real difference to be due to the number of electrons which compose it. We must understand that these revolving electrons are locked up within the atom. We cannot interfere with their energy. We may heat the substance, composed of the atoms, to a temperature of thousands of degrees, or we may chill it down till its temperature reads 300 degrees below zero on the Fahrenheit scale, and yet the atoms remain as before. The substance will, of course, alter from a solid to a liquid or a gaseous condition, or the other way about when cooling. But an atom of gold remains always an atom of gold, and an atom of hydrogen cannot be changed into anything else. Atoms have been called the little bricks of nature. The electron theory has added to this picture, for now we have some idea of what these invisible bricks are composed. In very rare cases we see evidences of an atom breaking up, and some of the electrons escaping from within the atom. The most notable case is that of radium, of which we read in an earlier chapter. But I have mentioned electrons flying across an X-ray tube. Where did these come from? It is quite evident that they cannot come from the inside of the atom. They must have been outsiders. We have ample evidence that there are a great many electrons which are attached only in a temporary manner to the atoms of matter. Indeed, we picture these as roving electrons wandering about from atom to atom. The old world experiment of rubbing a piece of amber with a fur or cloth has a new interest to us. We have caused a surplus of these roving or detachable electrons to leave the rubber and take up their lodgment upon the amber. We have added so many little particles of negative electricity to the amber that it shows an appreciable negative charge. A body charged with electricity has therefore a new meaning. If it is negatively charged, we picture a surplus of electrons upon its surface. There must of necessity be a corresponding deficiency of electrons on some neighboring body or bodies, and we describe this condition as positively charged. The transfer of electrons from one body to another affects the surface only. Long before we knew anything about electrons, we were aware that an electric charge resided only upon the surface. When we speak of a discharge of electricity, such as we see on a grand scale in lightning, we picture a sudden expulsion of electrons from one body to another. In the case of lightning, it is from one cloud to another, or between a cloud and the earth. When Volta made the first electric battery, he caused the atoms in the zinc plate to hand electrons along the connecting wire to the atoms in the copper plate. The electrons were handed on from atom to atom in the wire, each atom giving up a spare electron to its neighbor on one side as it accepted an electron from its neighbor on the other side. We therefore picture a steady flow of electrons along a wire, and we say that an electric current is flowing in the wire. These moving electrons disturb the ether of space surrounding them, and the energy of the electric current is carried really by the ether. It is well to take particular note of this, lest anyone should imagine that the electrons fly along the wire with the speed of the electric current. As a matter of fact, the rate of travel of the electrons may be measured conveniently in inches per minute or in yards per hour. The action, however, commences simultaneously along the whole line. When considering dynamos, we saw that we might produce either a continuous or an alternating current in the mains. In the former case, we set up a regular march of electrons from atom to atom along the line. But in the case of an alternating current, we cause the electrons to course to and fro from atom to atom, say first of all in one direction and then in the other. Of course, the surrounding ether will be disturbed, and energy will be transmitted just as in the previous case. In addition to these roving electrons, we picture others which revolve steadily around certain kinds of atoms, particularly the atoms of iron. These moving electrons produce magnetism. This helps us to extend the picture of a magnetic body which we considered in Chapter 4. But if moving electrons produce magnetic effects in the surrounding ether, we should expect a steady flow of electrons along a wire to produce magnetism also. We have known this to be a fact for nearly a century, although no reason could be assigned for it. It was a Danish philosopher who, in 1819, discovered that an electric current flowing in a wire set up a magnetic field around it. Possibly the repeated mention of this ether of space is rather mystifying to some readers. The nature of the ether is a very great mystery to every scientist. This does not mean, as some might suppose, that the ether is not a real existing thing. To all who consider the subject seriously, it is as real as the air they breathe. It would be better if we agreed to spell the name of this mysterious medium ether with AE instead of the much more common spelling ether with E. The word ether seems to take us farther away from any known form of matter, and it is quite evident that, whatever may be the nature of the space-filling medium, it is not any form of ordinary matter. One theory suggests that it is an infinitely light gas, while another demands for it a density greater than that of lead. The latter theory may appear, at first sight, to be quite ridiculous. But if we picture matter as holes in a very dense medium, the theory is not inconceivable. However, all that concerns us at present is that although the nature of the ether is a complete mystery, its presence is very real, and the part it plays in the universe is of primary importance. We know that light is simply waves in this all-pervading medium. We are familiar with the fact that a substance, when heated to an incandescent state, will set up these ether waves of light. Until quite recently, it was a mystery to us how atoms of matter could disturb the ether, for it is apparent that even huge lumps of matter, such as the planets, can move through the ether without any appreciable resistance being offered to their movements. Here we are on the back of a great planet, flying through space at the enormous speed of 1,000 miles per minute, and the ether does not disturb even our flimsy atmospheric blanket, which we carry wrapped around us in our great flight. The electron theory supplies the missing link between the ether and matter. We have experimental proof that there are satellite electrons revolving around their atoms, just as the moon revolves around our Earth. These satellite electrons make billions of revolutions per second, and in doing so they disturb the ether and produce those waves which we call light. If these satellite electrons revolve at a comparatively slow rate, they produce long ether waves. In other words, waves few and far between. These waves do not affect our vision, but they produce heat. We call them radiant heat waves, but of course they are not warm, they are merely waves in the ether. The sun sets up such waves and they reach us across the space of millions of miles, but that space is not heated. It is only when these ether waves fall upon matter that they produce the phenomenon known as heat. A flying bullet on the battlefield may produce pain when it strikes a soldier, but the flying bullet is not the pain. When the satellite electrons revolve at a speed sufficient to produce the short waves which affect our eyes, these waves give rise to a variety of sensations. A certain rate of waves produces the sensation of red, a higher rate gives rise to green, where a still higher rate stimulates the violet sensation. When all these waves fall upon the same part of the retina at the one time, we have that sensation which we describe as white. Another point upon which the electron theory has shed new light is the nature of chemical union. We have no doubt that chemical union is simply electrical union between the atoms of matter. It is really a case of electrical attraction between oppositely charged atoms. This adds a new interest to electrochemical actions. We see how it is that by passing an electric current through water, we get the atoms of hydrogen and oxygen to part company and escape as oxygen and hydrogen gases. We have answered, in some measure, the questions with which we set out, regarding the nature of matter, electric charges, electric currents, magnetism, light, and heat. It has only been possible to draw the very barest outline of the electron theory. The subject is so large that to give even a popular account of it requires a volume as large as the present one. I have endeavored to do this recently in a book called Scientific Ideas of Today. That the electron theory appeals to the general reader as well as to the scientist is witnessed by the fact that this popular account to which I have referred has gone into a third edition within its first year. Personally, I believe that the electron theory is the beginning of a new era of thought. End of chapter 32.
Chapter 33 of The Romance of Modern Electricity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Marie Christian. The Romance of Modern Electricity by Charles R. Gibson. Chapter 33. Conclusion. More wonderful than Aladdin's lamp. A brief historical review. Slow progress prior to the 19th century. An international advance. Davy and Faraday. A genealogical table. Present achievements. Future possibilities. We have seen how electricity serves mankind, enabling us to hold immediate communication with all parts of the world, or carrying for us the mighty power of the waterfall to distant towns by means of a stationary wire, or making it possible for us to actually hold conversations with friends distant hundreds of miles. Does not the simple statement of these and similar facts read as a fairy tale? And are they not, in truth, far more wonderful than all that Aladdin's lamp did for him? It is remarkable that all the practical applications of electricity have been made during the last century, and that the most of these have been begun during the lifetime of many people now living. Within the last decade, we have seen many new fields opened up in the electrical world, the most conspicuous applications being X-ray work and wireless signaling. The experimental work with radioactive bodies has also a close connection with electricity. Electricity had been known from early times, there being records relating to rubbed amber as far back as 640 BC, and the discovery of magnetism in the lodestone or natural magnet is a matter of ancient history, having been recorded at a much earlier date than the observed phenomena of electrical attraction in rubbed amber. It does seem strange that these phenomena, which have now led to such marvelous results, were allowed to lie practically dormant for a space of 20 centuries. During that long time, generations of men came and went, attaching little, if any, importance to these great discoveries, excepting to use the lodestone as a guide in desert marches. It was not until the dawn of the 17th century that any serious attention was given to this important subject. About the year 1600, Dr. William Gilbert, one of Queen Elizabeth's private physicians, wrote a book describing many experiments he had made, and deducing from these that the earth itself was a huge magnet, and that it was possible to magnetize a piece of iron by the earth's influence. Gilbert also suggested that terrestrial magnetism and electricity were both allied emanations of a single force. One very important discovery of Gilbert's was that amber, which had so long been known to possess peculiar properties when rubbed, had no monopoly of these properties, but that they were also exhibited by a very great number of bodies when rubbed. By direct experiment, Gilbert was able to show such bodies as glass, sulfur, sealing wax, hard wood, etc., attracting light bodies towards them after friction had been applied to their surfaces. But although Gilbert wrote down very clearly in Latin all that he had discovered and proved, the subject received very little attention for another century and a half. During that time, people had certainly taken some little interest, for they had constructed simple machines to do the rubbing for them on a larger scale, and with the increased effects, a few additional phenomena had been observed. But the advance of knowledge in this branch of science was extremely slow. It was Germany that gave the lead in the making of these early electrical machines. About the middle of the 18th century, Benjamin Franklin, the great American philosopher, discovered the identity of electricity with lightning, and before the century had closed, Professor Galvani of Italy made known his observations on the twitching of a dead frog's legs due to an electric discharge. His fellow countryman, Volta, a celebrated physician of Bologna, in following up the observations of Galvani, discovered a means of producing a continuous electric current. Progress now became more rapid, for with the dawn of the 19th century, a very close relationship was proved to exist between electricity and magnetism. We are indebted to the native land of Her Majesty Queen Alexandra for this very important discovery, for it was Hans Christian Ørsted of Denmark who observed the effect of an electric current upon a neighboring magnetic needle. About this time, Professor Ampere of France and Dr. G.S. Ohm of Germany, whose names are embodied in present-day electrical units, did much to make the meaning of things clearer. It was also about this same time, or to be more exact, in 1822, that Professor Seebeck of Berlin discovered that electricity could be produced by heat. While it was an Englishman who in 1600 laid the foundations of electrical science, it is clear that, after a long lapse of years, the progress was very materially aided by America, Germany, Italy, France, and Denmark. But when we come to a study of modern developments, we find two Englishmen taking a very strong lead. Indeed, we may look upon Sir Humphrey Davy and his co-worker Michael Faraday as the pioneers of all the great industrial applications of electricity. These two great men worked together at the Royal Institution in London, Faraday acting as assistant to Davy. It is interesting to note in this connection that although Davy was only Faraday's senior by a dozen years, he did not live to see any of the great electrical industries begun, while Faraday, who along with Davy laid the foundation stones, lived to see many electrical applications launched on a business footing, as he did not die till the year 1867. There is an interesting story told of Faraday, which serves to show his very practical turn of mind. An American inventor came over to this country in the early days of electrical enterprise, exhibiting a large electrical motor machine, with the object of floating the same for industrial purposes. A number of eminent men of the day were asked to give their opinions regarding this new kind of motor. Some gave great praise, but Faraday stood for some time watching the machine at work, and then, without making any remark, he went to the corner of the room, and picking up a broom, he applied the handle of it as a brake upon the large flywheel, till he almost brought the motor to a standstill. Then, letting it go free, he left without making any public statement. It must have been clear to the inventor that his motor was not capable of driving any load. Of course, this genius had no better source of power than a large and clumsy chemical battery. This review has purposely been very brief, and it is therefore necessarily incomplete, including merely those items of most general interest. A very simple genealogical table might be formed, beginning with lodestone and rubbed amber, the latter leading to the construction of frictional machines, then the discovery of the action of one of these machines upon the legs of a frog, it being found that the contact of two dissimilar pieces of metal produced the same twitching effect as the electrical machine. A battery of metal discs was made, and these placed in acids gave us the principle of all batteries. The observed effect of this battery current upon a neighboring magnetic needle gave the basis of all telegraph and telephone apparatus, and when it was discovered that the converse was true, and that a magnet could so influence a moving conductor as to set up an electric current in it, then dynamos, motors, induction coils, etc., soon followed. Lord Kelvin, Sir William Thomson, one of the foremost workers in the electrical world, has passed away since the date of the first edition of this volume. His ingenuity made submarine telegraphy possible. He added a great deal to our electrical knowledge. Professor Sir J. Thomson of Cambridge and Sir Oliver Lodge of Birmingham are conspicuous in connection with modern ideas of electricity. To sum up in detail the benefits we have already obtained from electricity would require considerable space and is quite unnecessary. It will be sufficient to remark upon a few of the principal applications. As a speedy carrier of news, electricity has no rival. It also holds a unique position in transmitting speech over great distances, and quite recently we have the almost inconceivable achievement of speaking through space without any connecting wires. While as an illuminant, electricity has rivals which successfully compete with it, it possesses many advantages over its competitors, the one obstacle to its general use being its greater cost. As a means of conveying power from one place to another, electricity stands head and shoulders above all other methods, making it possible to take advantage of the energy of large waterfalls. We have seen how electricity now aids the physician and the chemist, whilst a host of other interesting applications have been dealt with. It would be idle to prophesy regarding the future possibilities in the electrical world, but there seems little doubt that in time we shall have a complete electrification of our railways. Our present method of making the source of power drive not only itself along, but also a heavy supply of coals and water for its own consumption, does seem a very clumsy proceeding, when compared with a fixed generating plant dispensing power in wholesale fashion to all the trains upon a particular route. It is very remarkable that the trains have merely to be in contact with a stationary wire, which conducts current from the dynamos to the electric motors on board the train. We must look upon these motors as merely converters, transforming electrical energy into mechanical motion. There will, no doubt, be a great increase in speed on electrified railways, and it is quite possible that the ordinary speeds of the next generation would at present appear quite ridiculous to us if they could be correctly predicted. Our grandfathers said that people would as soon be shot off like a Congreve rocket as trust themselves to the mercy of a steam locomotive, the speed then being about 18 miles per hour. Nowadays we ride at a speed of 50 miles an hour, with an occasional short run of 90 miles per hour. It seems to me very probable that before another generation has come and gone, people will have no cause to grumble at smoke and dirt in the atmosphere of cities, as the whole energy required for motive power, heating, and lighting may be delivered from one great generating station outside of the city. When the cost of electricity has been greatly reduced, its use will doubtless become quite universal, and in future days the housewives will not have to trouble about the making of fires for heating and cooking. It may be that both the heating and lighting will be regulated by automatic devices, which even now would be possible, though extravagant. When using the telephone of the future, we need not be surprised if, when calling up a friend without the aid of exchange operators, we hear our friend's voice reply that he has gone out and does not expect to be back till late in the evening, but begs us, if it is any message that can be left for him, just to speak it into this automatic machine which is at present speaking, and it will deliver the message to its master on his return home. Doubtless there will be advances during the next century that the mind of man has not yet conceived, for the patient research of so many able workers is bound to be productive and leading to further practical applications. When Franklin was asked what use there was in some of his experiments, he would reply in Scotch fashion by asking another question: "What is the use of a baby?" And when the illustrious Faraday was similarly questioned, he would say, "Endeavor to make it useful." It was only yesterday we knew nothing of X-rays, wireless telegraphy, etc., and doubtless there are other and greater surprises awaiting even the present generation of men, while those things which we now class under modern electricity may ere long be catalogued as early ideas and undertakings in ether. End of chapter 33. End of The Romance of Modern Electricity by Charles R. Gibson.